Hello everyone, and welcome to 6-7, Geometric Sequences and Series. Today we're going to identify, write, and use geometric sequences and series, and we're going to use sigma notation to find the sum of geometric series. Alright, so I said this before, but this is probably one of the more difficult lessons that we're going to do all year. Okay, and if we just zoom back a little bit, this is it's going to be a bit of a longer one too. Okay, so grab your popcorn for your left hand, grab your pencil in your right hand, and enjoy the show, but also try to kind of just follow along as best you can, right? I kind of broke this down a little bit more than normal because a lot of these concepts are novel. So if you want to put me on 2.5 speed or something like that, if you think that's helpful in certain places, please do so. All right. So let's start off with what is a geometric sequence. We already learned arithmetic sequences. Arithmetic sequence was, they had a common difference, right? So we'd have like 1, 2, 3, 4, 5, and then sometimes we would add all those numbers together, right? But an arithmetic sequence has a common difference because from one to the next, you were adding or subtracting the same number each time. Well, a geometric sequence is where you do the same thing, but instead of adding or subtracting each time, you're multiplying each time. Okay, so let's look at this number here. So we have 4, 12, 36, 108, 324, right? We're clearly multiplying by 3 each time. All right, which makes this a geometric sequence, but that's what we're going to talk about here. So a geometric sequence shares a common ratio, r, between consecutive terms. So we have the term number, which we call n, like this would be n to the 1, n2, n3, n4, n5, and then a to the n is the value of the term. So in other words, this 4 here, n would equal 1, right? A sub 1 is 4, right? For 12, n equals 2, a sub n is 12, right? So that's what this means. Where n is 3, a sub n is 36, right? And you'll notice also that we keep multiplying by 3 to go from piece to piece, which means our common ratio is 3. And we represent the common ratio as r. And this is very important because this is one of our key pieces for all the formulas that we're going to be using going forward. So this is a geometric sequence. And the important takeaway is that we need to know what n means. N means the actual number of the term. And a sub n is the value of our series at the nth term, right? So in other words, in the 4th spot, we have a 108, right? So a sub 4 is 108. All right, recursive definition. So the recursive definition we don't use as often, but it's a good way of showing us exactly what's going on step by step. That way when we go into the explicit formula, we kind of know where everything's coming from. So the recursive formula is at a sub n equals, well, where it equals a is at n equals 1, right? So a sub n equals a at n equals 1, which makes sense, right? If n equals 1, then whatever a is what a is going to be. Now, at anything a sub n equals r times a to the n minus 1 at where n is greater than 1. In other words, for our initial point, right, a sub 1, n is just going to equal 1. For every other point, it's going to be r times the previous value, right? And that's kind of how a recursive formula works, is you're kind of showing step by step by step what each individual step is doing, right? And this formula is a little bit confusing. It's honestly even slightly confusing to me, right? It's not intuitive, right? But when you see these problems pop up, you'll see what it's doing, and it's almost easier to understand what it's doing more than to understand what these pieces are, and then kind of look back at the formula and you'd be like, oh, okay, that kind of makes a little bit more sense now. All right, so let's write the recursive definition for this sequence. We have 12, 9.6, 7.68, and 6.144, and then this will go on forever, right? Okay. So the first thing we're going to do is we're going to find r. Now we're going to find this as a common ratio. And the common ratio, if we go back over here, right, the way we did this is we did, okay, 12 divided by 4 is 3. 36 divided by 12 is 3. 108 divided by 36 is 3, right? So that's how we find the common ratio. So you'll notice that I wrote it here is we can use any of these, right? We can say a sub 2 over a sub 1, right? Which is what we did here, 12 and 4, right? A sub 3 over a sub 2 would be 36 divided by 12. If this is geometric, these will all have to be the same, right? So if a problem tells you that it's a geometric sequence, you can find the common ratio by simply dividing one term by its previous term, right? So 9.6 divided by 12, right? And that'll give you the common ratio. So that's, if you look down here, you'll notice that 9.6 over 12, 7.68 divided by 9.6, and 6.144 over 7.68, those all equal 0.8. So 0.8 is our common ratio. And if you want to know if something is a geometric sequence, you can take these terms and keep multiplying them backwards to get the pattern, right? And as long as they all keep showing up with the same value for r, you know that we're good. So if we want to rewrite this, right, well, we have where n equals 1, a sub n just equals a. Well, what is where n equals 1? Well, where n equals 1, we have a 12, right? So a sub n equals 12 when n equals 1, right? In other words, a to the 1 equals 12, which makes sense, right? A to the 1 is 12. Okay. Now, this other part's a little bit more confusing, right? But what it's saying is that when we're taking our common ratio and we're multiplying it by whatever our last term was, because this would be n minus 1, so this would be our last term. So let's say for instance, like n is 4, right? Let's say we're trying to find our fourth term. In order to find the fourth term, we're going to take the 4 minus 1, so we're going to take the third term, right? And this is the whole point of this, right? In order to find the fourth term, we're going to take the third term and we're going to multiply it by 0.8. In order to do that, we need to have found the second term, and we would have need to have found the first term. And I'm going to show you an example of this here in a second, but the idea behind the recursive formula is that you're essentially just, you're doing one step, and then you're like, okay, well, in order to do the next step, now I multiply by 0.8. Okay, now in the next step, I multiply by 0.8, right? But you have to do step by step by step, because in order to know the next step, you have to know the step before. That's kind of how recursive works. All right. Now we're going to talk about the other kind, which is called explicit, and I'm going to show you a recursive formula and like show you how it turns into a recursive formula, so that I'm going to show you a explicit formula and then show you how a recursive formula goes into an explicit formula, so that you can, like, I'm going to show you all of this, right? In terms of the math, you see it kind of over here. I'm going to show you how this works. So, all right, converting between recursive and explicit definitions. So the explicit formula is this. And this is going to be kind of intuitive because that's what we just said, right? We have a sub n. In other words, let's say we're finding the fifth term, right? What we're going to do is we're going to take our first term and we're going to multiply it by our common ratio to the power of n minus 1. In other words, how many terms have we done so far? And that makes sense, right? Like if I want to, let's go back here. If I want to know the fifth term, right? What I'm going to do is I'm going to take my initial a sub n, right, a sub 1. I'm going to take 4. Well, I know the common difference is 3, and I know I did this 4 times to get to 5. So I'm going to do 4 times 3 to the 4th power, right? I need to do 3 times 3 times 3 times 3, and then multiply that number times 4, right? And that's how we get 324, right? And that's what we're doing up here with the explicit formula. Now, like I said, if that didn't make sense, just let's do a problem real quick. And then I think it'll click a little bit faster, because you'll see what I'm talking about. So convert into explicit. So if we have a to the n equals 5 at n equals 1 and equals 1/2 times a to the n minus 1, where n is greater than 1, right? There's a few important pieces of information we know here. First of all, we know that our r, right, if we go back here, our r is this first number being multiplied. We know that our r is 1/2. So that's very important. We also know that our a sub 1 is 5, because that's what we put here as our initial value. So the 5 and the 1/2, those are the big numbers that we care about from our recursive definition, right? Our recursive formula, we know that this is a sub 1, and we know this is r. All right, so now let's use the recursive formula. I'm going to show you how the recursive formula works, and it will show you how the explicit formula is like generated. So all of the stuff I've been talking about before, I'm going to show you an actual problem now. So really pay attention now, because I think this will help make the other stuff click a little bit. All right, so let's use recursive to show explicit. So we know a sub 1 is 5, right? Our initial value here is 5. We talked about that. Now, a sub 2, right? I mean, remember, what we're doing is we're taking our initial number and we're multiplying it by the common ratio, right? That's all we're doing. So 4 times 3 is 12. So here we know that we have 5. So 5 times 1/2, that'll give us our second term, right? So that's what this is. A sub 2 equals 5 times 1/2, right? Well, a sub 3 is this whole piece, 5 times 1/2, whatever that was, times 1/2, right? Because we're going to keep multiplying it by 1/2. So a sub 3 equals a sub 2 times 1/2, right? Which equals 5 times 1/2 times 1/2, which equals 5 times 1/2 squared, right? Because we're taking 1/2 and multiplying it by itself, right? So this becomes 5 to the 1/2, or 5 times 1/2 squared. Okay, so that was a sub 3. A sub 4 is going to be this times 1/2, right? Because we're just multiplying it again. So a sub 4 is going to be a sub 3 times 1/2, right? Remember, a sub 3 was 5 times 1/2 squared. So 5 times 1/2 squared times 1/2 equals 5 times 1/2 cubed, right? And you'll notice here that this 3 is always going to be one less than the term we're trying to find, right? Which means that if we look at our explicit formula for this function, or for this sequence, it's a sub n equals 5 times 1/2 to the n minus 1, right? N minus 1, because if we're looking for the fourth term, we're going to raise it to the third power. And then n, because that's the number we're looking for, right? So in other words, if we're looking for the fifth term, right, what this is going to be is 5 times 1/2 to the 5 minus 1, which is 4. So we're going to do 5 times 1/2 to the fourth. And that would give us our fifth term. All we'd have to do is multiply that out. We'd know exactly what our fifth term is. Okay? All right. So let's use the geometric series here. Let's try a problem. Okay. So a phone chain is when one person calls a certain number of people, and each of those people then call the same number of people. If we know in the first round 3 people were called, and in the fifth round 243 people were called, how many people were called in each round? Okay. Well, let's take a look. So first thing we're going to do is set up our explicit formula, right? I rewrote that out here, right? A sub n equals a sub 1 times r to the power of n minus 1. Now, we know that first round 3 people were called, so we know that a sub 1 is 3, and we know in the fifth round, right, 243 people were called. So we know a sub 5 is 243, right? These are the things that we know. Okay, so what we're going to do is we're going to say, okay, let's start with the fifth, right? Let's just talk about the fifth round. We know that 243 is a sub 5, right? So if we go back here, right, what we're doing is we're finding a sub 5 first. Does that make sense? So we're going to set a sub 5 here. So 243 equals our initial value, which in this case is 3, because 3 was our a sub 1, times r to the 5 minus 1, right? Because we're talking about the fifth term, so this would be 5 minus 1. So we're going to raise it to the fourth power, essentially, right? So really what this question is asking, right? If you're wondering what the question is asking, how many people were called in each round? What is the common ratio, right? What are we, like, how many people are we doing this for? Like, how many people are making these calls, right? So, well, first of all, we know that 3 people were called, right? And then we know, right? We know that if 3 people are called, then 3 people are called each time, right? So we already kind of know that the common ratio is 3, right? So maybe you could have done it that way too. But this is what we're going to do for this to try to solve for r, right? So we have 243 equals 3 times r to the fourth, right? So first thing you're going to do to get r to the fourth by itself is divide by 3, and then you'll get 81 equals r to the fourth. Take the fourth root of both sides. The fourth root of 81 is 3. So r equals 3. Therefore, right, that's what these 3 dots mean is therefore, a sub n, right, if we actually talk about our formula for this, to set up our explicit formula, a sub n equals our initial value, which is 3, times our common ratio, which is 3, to the n minus 1. Now we can use this formula to find a sub n at every level of n. If you want to know 350 chains down the road, how many people have been called, we can put in a sub 350, I think that's the number I said, a sub 350 equals 3 times 3 to the 349, right? And that will tell us how many people have been called. So how many people were called in round 8? Well, let's figure it out. We have a sub 8, right? Because that's the nth term. The nth term is 8 in this case, of our initial value, which is 3, times our common ratio, which is 3, to the 8 minus 1, which is 7, right? So a sub 8 equals 3 times 3 to the 7th. Remember to always do the 3 to the 7th first, right? Like this number has to be resolved before we multiply it by this 3. So we typed that in our calculator, and a sub 8 equals 6,561 people. So at 8 rounds of, 3 people calling 3 people, and then those people calling 3 people, after 8 of those, 6,561 people will have been called. Okay. So the reason why this is important is because we can use the explicit formula to solve for any of these pieces, right? We can solve for a sub n, we can solve for a sub 1, we can solve for r, right? We can solve for all these things. We can even solve for n technically. All right, let's talk about sums, okay? In other words, if I wanted to take, let's go back to this initial function, right? If I wanted to know all of these terms, right? And let's say I wanted to know all the way to like 100, and I wanted to know what the sum of all of these numbers are. I wanted to know what 4 plus 12 plus 36 plus 108, I want to know what the sum of all of those are, okay? Because that might be useful. Like, I know back when we did arithmetic series, we had a problem where we knew that we were in a movie theater, and like the first row was like 10 seats, and then every row after that was an extra 2 seats. And we wanted to know how many total seats there were in 20 rows, right? It's very useful to be able to add them all together. It's actually one of the more real life uses of it. So, all right. What is sigma notation? This is the way we talk about sums. We talk about sum with sigma notation. So, sigma notation is a quick way of expressing the sum of terms. Now, this is going to look Greek. It actually might be. But the point is that this term here, this little backwards E looking thing, this means sum. So when you see this, it's basically saying the sum of all of these terms that we're about to talk about, right? We're finding what they are all added together. So what these terms mean is if we have our function f of k, right, where k equals a, this is our lower limit. In other words, for everything we've done so far, we've been talking about from a sub 1 all the way up through the final term, right? So a sub 1 was our lower limit. Does that make sense? And then b is the highest number. It's our upper limit, right? So from a to b at this function is what we're finding. And we're going to do a few problems, right? This isn't, I promise, this is, we're going to get into this a little bit more. But it's our function from a to b. It's the sum of our function from a to b at all of those terms. The value at each of those terms all added together. All right, so these are all, like, index of summation, it basically means the function, right? And then f of k is the function that's being summed, right? This is what we're talking about here. This is the key takeaway. All right, so let's talk about this. Let's solve, right? Let's solve the sum of k from 1 to 4, right? Now, k is the same, it's just a variable, right? If you think about this as like, if f of x equals k, right? Well, what would that look like on a graph? If we go back here, right? And we go to, let's just type it in here. If I have k, right? Or y equals, it's the same thing as y equals x, right? It's just a variable, it's just a letter, right? We're getting a line. Does that make sense? So what we're saying is from 1 to 4, what would our sum be? Well, when k equals 1, what is k? Well, it's just 1, right? It's so simple that it's actually like kind of confusing. But the idea is that where k is 1, so our first term is 1. Where k is 2, our first term is 2, right? Our term is 2, so we have a 2. And then 3, and then 4, right? We're going from 1 to 4, and we're evaluating k at each of those places, right? So k is 1, k is 2, k is 3, k is 4. Now we add them all together. That's what the sum symbol means. So 1 plus 2 plus 3 plus 4 is 10. So the sum of k from 1 to 4 is 10. Okay? This is just going to take some looking at, take some practice, okay? So the sum of k, where k is from 1 to 4, is 10. Let's try one that, this actually may be a little bit more intuitive for some people, because k, the whole k thing is a little bit odd, right? So let's find the sum of n squared from 1 to 3. Okay? Now, the way we're going to do this is we're going to take n, we're going to substitute each of these numbers between 1 to 3, n for n. So we need to know n sub 1, n sub 2, and n3, right? So n1 would be 1 squared, which is 1, right? N2 would be 2 squared, which is 4. And n3 is going to be 3 squared, which is 9, right? So what we're going to do is we're going to do 1 squared, 1, 2 squared, 4, 3 squared, 9. And we're taking the sum of those numbers. 1 plus 4 plus 9 is 14. So to solve the sum of n squared from 1 to 3, it's going to equal 14. Hopefully this one, I think this one might actually be a little bit more intuitive as to how it works. But now if you look back at this one, it will make a little bit more sense, right? This is just a number. This is just x. So we're going from 1, 2, 3, and 4, right? 1 plus 2 plus 3 plus 4 is 10. So we're just adding all of those numbers together. All right, that's the very basics of it, right? We're going to touch on what this means for our geometric series here in a second. But just know that basically we're taking this function, this is our lower limit, this is our upper limit, and we're doing everything in between. Okay? All right, so let's go give it a shot here. So first we're going to talk about our formulas and how they relate to geometric series. So know that the term finite means that it ends, right? You can't find the sum, well, you can, but we're going to only be talking about finding the sum of terms that have a fixed number, right? Because if I told you that the series goes on forever, right? How would you even find the sum of that, right? That's much more complicated math than what we're going to do this year. So we're going to find the sum of terms only up to a certain point, okay? And it's going to tell you what that point is, right? It's always going to tell you what our final term is, right? Do you see how this one had a 4? And then we get on here and it was a 3, right? That's our final term. That's as far as we're going. So we're only talking about finite geometric series, not infinite geometric series. Okay, so a geometric series is the sum of the terms in a geometric sequence. So a sequence is just a set of numbers. A series is the sum of those numbers. So finite sum formula, and this is derived from, there's actually a really cool derivation in your book if you want to look at this. It's actually really neat. But the finite sum formula is the sum of n terms, right? So in other words, all of the sum of all of those numbers is our initial value, a sub 1, to the 1 minus our common ratio to the nth term, right? So in other words, if we're finding the sum of 6 terms, this n would also be a 6, right? Whatever the n is down here, it matches the n that's up here. And this is over 1 minus our common ratio, right? So this is our formula. If we use this, we can find the sum of all of these terms in our geometric series. Okay, so S sub n equals the sum of the terms, r is our common ratio, a sub 1 is the first term, and then n is the number of terms that we're using. It's our upper limit, right? It's our total number of terms. So the sigma notation for this formula, right, and this makes sense, our initial value times r to the n minus 1. So you'll see that this looks a lot like our explicit formula, because it is, right? So it's our explicit formula from a range of n equals 1 to n, and n is the s of n term. So like we don't know what this is until we jump into the problem, right? This could be 6, it could be 10,000, right? This is our upper limit, right? Okay, so this is what this means. So let's go and give it a shot, right? I'm feeling confident about this. So using the finite sum formula to solve, we're going to put the geometric series into sigma notation, and then we're going to find the sum. So this is our series here, okay? These are our terms. There's no dot, dot, dot. It doesn't go on forever. It's just this. So we have 1, 2, 3, 4, 5, 6. We have 7 total terms, right? So we need to find our key pieces, right? We need to find all of these things. We need to find a sub 1. We need to find r. We need to find n, which we just found out was 7, right? That's not too bad. And then we're just gonna sum everything together, okay? So first of all, how can we find these? Well, we know a sub 1 is 3. That's not too bad, right? So we can plug that in, right? We know that we have 7 terms, so we can plug in the 7 for the n. Initial term is just n equals 1, right? In other words, we're not like just starting at this 2 for some reason. We're going to start at the 3. So n equals 1. And then the other thing remember we talked about before, the common ratio. The common ratio is this term divided by this term. If we go back all the way, right, to here, right, to find the common ratio, we have to take one term and divide it by the term before it, right? And you can do anything you want. You could do 32 over 81 divided by 16 over 27 if you really wanted to. I decided to do 2 divided by 3 because that seemed a lot easier. But yeah, feel free to be as bold as you'd like. So yeah, so our common ratio is 2/3, right? Because it's going to be 2 divided by 3, right? 4/3 is just this divided by 2/3, right? You're going to divide by 2/3 each time. Okay, so our common ratio is 2/3, and then of course to the n minus 1. But in this case, we know that n is going to be 7, right? All right, so we're going to find the sum. And all we're going to do is we're going to take the information we just got with this formula, and we're going to plug it in, right? So if we take we know that we're finding the sum of 7 terms, right? That's our upper limit here. This is going to equal our initial value, which we already know is a 3 up here. Like if we go all the way up here, it's a 3, right? To the 1 minus our common ratio to the nth power, which in this case we said was 7, over 1 minus our common ratio, which is 2/3. So what this will do is this will turn into 3 times 0.9415. Just trust me on the math. I just put it in a calculator, right? And that's all divided by 0.333. So the sum of 7 terms of these 7, if we add all of these together, you get 8.473. Now, what's a good thing to always do when you get an answer is double check, does this make sense, right? Clearly our numbers are getting smaller, right? We're going 3 to, this is like 1.33, right? This is not even 1, right? So 3, 4, 5, 6, and then these are just going to keep getting smaller and smaller. Does 8.5 kind of make sense for this? I think it definitely does, right? 3, 4, 5, 6, this is going to be less than 1, even more less than 1, right? You're getting to the point where it's less than a half at some of these, you know what I mean? So it's getting really, really small. This is almost a fourth, right? So we're getting really, really, really small. So yeah, it makes sense that we're going to be losing some. The graph is going to like go down like this, right? So yeah, 8.473 definitely makes sense. So we should feel pretty confident about that answer. All right. So guys, we're almost there, okay? we're almost there, I promise. 2 more things. The application is a lot of fun, so hopefully you stuck around for that and you got your popcorn out. And if you want to just watch me do the application, that's fine. You've already done the bulk of the learning. I just thought the application would be nice because we can use it to find n, which is something we're not going to do really as much. So, all right, finding the number of terms in a finite geometric series. So let's say we know the geometric series is 200 plus 300 plus 450 plus a bunch of other stuff, and then it ends up at 7,688.17. So we don't know these middle terms, and we don't even know how many terms there are, right? All we know is we start at 200, we end up at 7,688.7, and we're adding all those up, right? So, well, it doesn't even say that we have to add them all up yet. So this is why we've been learning logs and why this is in the log section. So let's plug this into our explicit formula, okay? Our explicit formula is going to be 7,688.7, right? In other words, our it's all the way back here, isn't it? Yeah. So hopefully you have this written down somewhere, right? But our explicit formula is, where are we? There we go. It's our final term equals our first term times our common ratio to the n minus 1, okay? So that's what we're going to be using here. I'm just going to say what they are, and then hopefully you can relate that to what they are. So 7,688.7 is our final term, our nth term. We don't know what it is, right? We don't know what n is, but we know that it is that term. This is going to equal our initial term, 200, times our common ratio, which is 1.5, which I found from just doing 300 divided by 200, right? That's 1.5. So 200 times 1.5 to the n minus 1. And again, we don't know what n minus 1 is, right? We don't know what this n is. Well, we know what minus 1 is. We don't know what the n is, right? So if we have this function, right, the first thing I got to do to get this n by itself is divide by 200. So I'm going to divide both sides by 200, and that's going to give me 7,688.7 divided by 200 is 38.444, and this equals 1.5 to the n minus 1. And oh my gosh, we have an exponent in our, or we have a variable in our exponent. How can we deal with that? We use logs. That's outstanding. I'm so happy. All right, so we're going to take the log of both sides, right? Remember, we learned that in the last lesson, that this is the reason we've done all this work is that we can learn how to take the log of both sides. So with the log of 38.444 equals the log of 1.5 to the n minus 1. The reason why we do this is because now we can take this n minus 1 and move it out of the exponent and pull it out in front of the log, right? So we have log of this equals n minus 1 times log of 1.5. Log of 1.5 is just a number, and we need n minus 1, so we can divide by log of 1.5, right? So log of 38.444 divided by log of 1.5 equals n minus 1, right? Because that's all we have left. Now we're just going to add 1 to both sides, because we don't need this 1 anymore. So log of 38.444 over log of 1.5 plus 1 equals n. In other words, n equals 10. So we know that there's 10 terms. And in fact, if you really if you wanted to brute force this, right? If you didn't want to, you're like, I will not do logs or any of this math, right? If you really wanted to do that, what you could do is, well, we know our common ratio is 1.5. If you want to take 450 and multiply that by 1.5, and then take that number and multiply it by 1.5, and then take that number and multiply it by 145.4, whatever, and you want to keep doing that all the way up until you get 7,688.7, go ahead. That's all you, right? You can do that. Absolutely. And then you'd figure out, oh, it took me 10 times to do this, right? So you could do that too if you have all day, or hopefully that n isn't to like 300, because you'd be there for a while, right? 10 is relatively manageable, but that number could get huge. So yeah, that was awesome. I love that problem, because not only did we get to use our series to find n, we got to use logs in a real problem. It's always tons of fun. All right. Application. Now we're gonna do a problem that is going to look like a mess. I would advise sticking around for this problem, because we are going to talk about some stuff that we haven't really talked about too much. We've touched on it, but we haven't really done it in the form of a problem, so this might be helpful. This might be one where you just get out the popcorn and kind of watch, right? If you want to take notes, absolutely do, but this would be a good one just to kind of watch. So Isabel needs to borrow to purchase a share in a food truck business. What will be her monthly payment? So they give us the formula to calculate the monthly payment. So our total monthly payment is going to equal the total loan, which is our principal for P, right? So this is where A is the monthly amount, P is the principal. So that's how much that's how much the loan is, right? And then here it says N is the number of months and I is the monthly interest rate. Now these things are critical to understand, right? We're calculating the number of months, right? The number of months. I don't know why these moved. That was interesting. And the monthly interest rate, right? I wanted to highlight these because up here it gives us some of these numbers, right? It says 24,000 for 6 years. Okay, this is a very inexpensive food truck, actually. 24,000? That sounds pretty cheap. But anyway, for 6 years, annual interest rate is 4.5%. What are they asking us for in the problem? Like, what is our I in this problem? It's our monthly interest rate. They gave us the annual interest rate, right? So we can't just plug in 4.5. That wouldn't work, right? Well, plus it's a percentage, but you get the idea. And N is the number of months, right? N isn't the number of years. We can't just plug in 6 for N, right? We have to do a little bit of understanding what the problem's asking us, right, in order to make this work. So first thing I'm going to do is try to define as many of my variables as possible. So P we determined was the principal. In other words, how much is the loan? So in this case, it's 24,000, right? So that's easy. We don't have to do anything with that. The amount of the loan is the amount of the loan. The other stuff is talking about how often we're going to be paying it, right? So N is the number of months. Well, that's not too bad, right? 6 years times 12 months, 72 months. So N is 72, okay? Now, our monthly interest rate is going to be our annual interest rate, which is 0.045, right? We have to turn this into a decimal, divided by 12, right? Because we're going to be doing it each month. So the 0.045 divided by 12 is 0.00375, right? So these are the terms, right? This is, I guarantee you, a lot of you guys would have just right out of the get-go, maybe made this mistake, right? And that's understandable. But that's why this problem is awesome, right? Because we can learn these kinds of things and what we have to do. We have to learn how to apply them into real world situations. All right, so you'll notice that the denominator down here, right? This formula contains a sum, right? So it's what the sum of all of this is, Our principal divided by that sum is going to give us our monthly payment. Okay, so we need to solve down here and then basically take 2,400 and divide it by that. And that'll give us what our monthly payment is. Okay, so let's plug in the stuff we know. We know n, our highest term, right, up here, is 72. We already figured that out, right? 1 plus 1 over I. Well, we know I is 0.00375. To the k, right, k is going to just be, it's going to be the term, right? So in other words, we're starting at 1, we're going to go 1, 2, 3, 4, all the way up to 72, right? So this would be a pain in the neck to do in any way other than the way we're about to do it. So, okay, so this is our sum, right? This, if we take this piece right here and we just enlarge it to where we can see it, it's right here, right? The 1 over, and then this is 1.00375 because it's 1 plus this, right? So this is our sum. All I did was take what they gave us, I figured out what these numbers are, and then I plugged them all in. All right. So to find a sub 1, we substitute 1 for k, right? In other words, this is something we haven't had to do yet, but if we're finding our initial term, we just need to know what this value is when k equals 1, right? So in other words, at our first term, what is this? Well, it's simply just 1 over 1.00375, which is 0.996. So our a sub 1 is 0.996. We need to know this because when we take this thing and we plug it into our sum formula, right, the one that we learned here, we need to be able to know what our a sub 1 is. So we find a sub 1, we get 0.996, and now we need to find our common ratio, right? So in order to find our common ratio, we do a sub 2 over a sub 1, right? Or we do a sub 3 over a sub 2. But here's the thing, we don't know, we weren't given a list of numbers, right? That's why this problem is cool, is because we have not been given a situation in which we don't have a series of numbers. They just told us that this is going to be the formula. But we can find the second number the same way we found the first number, right? If we found a sub 1 by plugging in 1 for k here, right, we essentially didn't have to worry about all of this because anytime you raise something to the first power, it's going to be itself, right? So if we take this number, right, we took the k, made it equal to 1, and we solved. If we take this k and make it a 2 and then solve, we'll find a sub 2, right? So we can find a sub 2 so that we can do the ratio between a sub 1 and a sub 2, so that way we can find the common ratio, right? So to find r, we need a sub 2 over a sub 1, right? That's what we need. So we can find a sub 2 by subbing in a 2 for k. So here we have 1 over 1.00375, but all of this squared, right? And when we solve all of this, we get 0.993, right? So we had 0.996. Now for a sub 2, we have 0.993. So we can do 0.993 over 0.996, and that'll give us our common ratio, which in this case is also 0.996. I mean, it goes out a little farther. They're not the same number, but when we round it to 3 decimal points, it's effectively the same number. So, all right, now we can use our explicit formula to find the sum, right? If we want to find this, we can use our explicit formula now, right? We know that a sub 1 is 0.996. We know n is 72, right? And we know r, which we just found, is 0.996. So our a sub 1, 0.996, times the quantity 1 minus 0.996 to the 72 over 1 minus 0.996. This will give us approximately, right? If you just do the math in here, you'll get approximately 62.417, right? So this is the sum of these 72 terms, right? This 62.417 is all of this right here, right? 62.417. Okay, so now what we're going to do is, because the formula tells us to take our principal and divide it by that, so we're going to take the number we just found, and we're going to take our 24,000 and divide it by our 62.417, and that is going to give us approximately $384.51 per month. So for 6 years, she's going to be paying almost $400 to pay back her loan for this food truck. All right, so not too bad, right? Setting this up was complicated, right? And then this is the kind of the thing that I really think is instructive, or is most instructive, is the idea that if we can plug in our n, right? We can find what we want our n to be. So if we know where k equals 2 and we know where k equals 1, we can find a sub 2 and a sub 1 in order to find the common ratio. And once we know the common ratio and our initial value, it's a done deal, right? Like we have everything we need. Well, we need n, but they gave us that initially, right? So we have everything we need to be able to find the sum of these 72 terms, right? And that's what we did. We took all 72 terms, we summed them together, and then took that number and divided 24,000 by it. All right. I know this has been a long video. I appreciate you sticking with me here. But what did we talk about? Let's go back. So we started off by talking about what a geometric sequence was. We discovered it has a common ratio because we keep multiplying that number over and over again. We then talked about recursive formulas, which we're not going to use too much, but we talked about recursive formulas and showed how we can use that to create an explicit formula. Once we know our explicit formula, we can talk about geometric sequences, and we can talk about actually finding the sum of these things, right? This was us just plugging in, using the explicit formula to solve a problem. And then we used sigma notation to understand what sums are, and we understand that sigma notation is an easier way to write the sum. And then we took our finite sum formula, and we plugged that into the sigma notation, so that now we have a form we can use to actually solve more complex problems. And then we just kind of solved a few things, right? We took this finite series, and we found the sum of that. And then we found one where we were looking for n, and we got to use all these really cool logs. And then we found out how much Isabel needs each month to pay for her food truck. So we did apply it to a few problems. This is a very interesting lesson that kind of uses a lot of the math we've learned, but it doesn't really tie to a lot of things. It's kind of its own like standalone thing. But we got through it together. So, all right, that's it. That's it for Unit 6. Now we're on to trig. I'll see you there.